For millennia, humanity has looked up at the night sky, captivated by the glittering tapestry of stars. From ancient mariners charting courses to modern stargazers simply seeking solace, the celestial sphere has always held a profound allure. It's a canvas of unimaginable scale, populated by suns many times larger and brighter than our own, burning billions of miles away. Among the most iconic and often asked questions, especially by children, is, why do stars twinkle? It seems like such a simple observation, a fundamental part of their charm. Yet the answer, like so much in science, reveals a fascinating interplay of cosmic distances, the properties of light, and the very unique characteristics of our home planet. We perceive stars as tiny, brilliant points of light, each a distant sun, and indeed they are. Their light travels across unimaginable voids of space, often for hundreds, thousands, or even millions of years before finally reaching us. When we observe them from Earth, they appear to flicker, shimmer, and dance in a way that planets, interestingly, do not. This twinkling, this beautiful celestial ballet, isn't actually happening at the star itself. It's not a cosmic wink, nor is it a sign of a star dying or being reborn. The stars themselves are, for the most part, emitting a steady, constant stream of light. So if the stars aren't twinkling, what is causing this mesmerizing effect? The secret, it turns out, lies much closer to home than you might think. It's an intricate dance between starlight and our very own atmosphere, a dynamic, turbulent envelope of gases that surrounds our planet, acting as both a protective shield and, in this case, an optical disruptor. Understanding this phenomenon opens a window into the physics of light, the dynamics of air, and even the challenges of modern astronomy. Imagine a star hundreds of light years away, a colossal nuclear furnace consistently blasting out photons in every direction. That light, once it begins its epic journey, travels unimpeded through the vacuum of space. It's a steady beam, as unwavering as a lighthouse beacon on a calm night. However, this perfectly stable stream of light encounters its first significant obstacle when it reaches Earth's atmosphere. Our atmosphere isn't a uniform, crystal-clear pane of glass. Instead, it's a swirling, ever-changing ocean of air, a complex system driven by countless factors. Think of our atmosphere as having multiple layers, each with varying temperatures, pressures, and densities. Sunlight heats the ground, which in turn warms the air above it. Warmer air rises, cooler air sinks, creating convection currents. We have winds, jet streams, and pockets of air with different moisture levels. All these elements contribute to making the atmosphere a dynamic and turbulent medium. It's like looking at an object at the bottom of a swimming pool that's constantly being agitated, or trying to see through the shimmering heat haze rising from a hot asphalt road on a summer's day. Each tiny parcel of air, whether it's warmer or cooler, denser or less dense, acts like a minuscule lens, slightly bending or refracting the light that passes through it. As starlight pierces our atmosphere, it doesn't just pass straight through. Instead, it encounters countless such lenses in rapid succession. The path of light is constantly being nudged, redirected, and distorted by these ever-moving pockets of air. This process, known as atmospheric refraction, is the key mechanism behind the twinkling effect. The light, which began its journey as a perfectly coherent beam, arrives at our eyes having taken a chaotic, zigzagging path through our planet's turbulent aerial envelope. So, how do these constant deflections of starlight translate into the twinkling we see? Imagine those countless tiny parcels of air, each acting like a mini prism or lens, constantly shifting and changing. As starlight passes through these turbulent layers, its path is not just bent, it's bent differently by each tiny pocket of moving air. Some light rays might be refracted towards your eye, others might be refracted slightly away. Furthermore, because different wavelengths of light, colors, are bent by slightly different amounts, a phenomenon known as dispersion, the star's light can also briefly split into its constituent colors, though this is usually too subtle for the naked eye. The key here is that stars, due to their immense distance, appear to us as mere point sources of light.
They are so far away that even through powerful telescopes, they resolve as incredibly tiny points. This means all the light from a star reaching your eye originates from a single concentrated beam. When this single concentrated beam is scattered and bent by the atmosphere, its intensity at your eye fluctuates dramatically and rapidly. One moment, a bundle of refracted light rays might converge on your pupil, making the star appear brighter. The next moment, those same rays might be deflected slightly away, making the star dim or even momentarily disappear from your perception. This rapid fluctuation in apparent brightness, combined with the tiny, swift shifts in the star's apparent position on the celestial sphere, is what we perceive as twinkling. It's not the star itself changing, but rather our own atmosphere playing tricks with its light. This also explains why planets typically don't twinkle. Planets are much closer to Earth, and even though they reflect light from our sun, they appear as disks rather than point sources. A planet presents a larger angular size to our eyes. So while some rays from one part of a planet's disk might be deflected away by atmospheric turbulence, other rays from another part of the disk will still reach your eye. It's like having many parallel beams of light. The atmosphere can't simultaneously block or deflect all of them at once, resulting in a much steadier, calmer appearance.
The twinkling of stars, while beautiful to the casual observer, actually poses a significant challenge for professional astronomers. When scientists try to capture crisp, detailed images of distant galaxies or exoplanets, atmospheric turbulence blurs and distorts their observations. It's like trying to read a book while looking through wavy glass. This effect is why observatories are often built on high mountaintops, far from city lights, and above a significant portion of the densest, most turbulent air. But even there, the twinkling remains. To overcome this, astronomers have developed incredible technologies. One such innovation is adaptive optics. This system uses powerful lasers to create artificial guide stars high in the atmosphere. Sensors then analyze how these guide stars twinkle and distort. A deformable mirror in the telescope, made of hundreds of tiny actuators, rapidly adjusts its shape thousands of times per second to precisely counteract the atmospheric distortions in real time. It's an ingenious way to counteract atmospheric distortions, allowing ground-based telescopes to achieve near-space telescope quality images. And speaking of space telescopes, the ultimate solution to atmospheric twinkling is to simply escape the atmosphere altogether. Observatories like the Hubble Space Telescope and more recently the James Webb Space Telescope orbit far above Earth's atmosphere. Freed from the interference of our turbulent air, they can capture images of breathtaking clarity and detail, revealing the universe as it truly is, without the shimmering veil that cloaks it from our terrestrial vantage point. These instruments allow us to peer back in time, unravel the mysteries of galaxy formation, and search for signs of life beyond our solar system, all by avoiding the twinkling effect. So the next time you gaze up at the night sky and watch the stars dance, remember that their twinkle is not a whimsical performance put on by distant suns. It's a testament to the dynamic nature of our own planet's atmosphere, a cosmic optical illusion orchestrated by winds, temperatures, and light traveling across unfathomable distances. It's a beautiful reminder that even in the simplest observations, there's a universe of complex science waiting to be discovered. The twinkle of a star is a poetic fusion of cosmic grandeur and earthly physics, a constant invitation to look up, wonder, and understand. Subscribe to the channel and hit the bell icon for more amazing videos.